Concrete is the most widely used human-made material on Earth, and it begins cracking almost the moment it hardens. Those cracks fuel a $4.5 trillion global repair cycle and feed into the 8% of carbon dioxide emissions tied to cement. Now, researchers have engineered self-healing concrete, a material with something alive inside it, designed to seal damage before it spreads. It all starts with one hairline crack. When concrete hardens, internal tensile stresses from shrinkage and temperature shifts inevitably tear the material apart at the microscopic level. These micro cracks initially appear harmless, but they function as direct pathways for destructive agents. Water carries dissolved road salts, acids, and chlorides straight into the concrete matrix, eventually reaching the internal network of reinforcing steel rebar. Once oxygen and water contact that steel, a destructive electrochemical reaction begins. The metal oxidizes and rusts. As rust forms, it expands to up to 6 times the volume of the original steel. This rapid internal expansion exerts immense tensile pressure on the surrounding concrete, cracking it from the inside out and causing the outer layers to break away in a process known as spalling. This continuous cycle of physical degradation lies at the heart of the $4.5 trillion global infrastructure maintenance burden. Repairing these compromised structures is not a permanent fix, but a temporary delay. Every patch, epoxy injection, and complete reconstruction requires fresh cement. Cement production relies on superheating limestone to over 1400 degrees Celsius. This releases carbon dioxide both from fuel burn and from calcination. Cement accounts for 8% of all global carbon emissions. Each reactive repair loop multiplies this environmental penalty. The structural vulnerability of concrete directly drives its massive carbon footprint, leaving engineers with a fundamental challenge. Instead of fighting cracks reactively, can we program the material to heal itself? At Delft University of Technology, microbiologist Henk Jonkers found the answer by treating concrete not as a dead substance but as a living habitat. His mechanism relies on a biological engine powered by Bacillus bacteria. During the initial mixing process, dormant Bacillus spores are embedded directly into the wet concrete alongside a solid, calcium-based nutrient that serves as their fuel source. In this spore state, the bacteria remain protected by a tough outer shell, allowing them to survive the crushing physical pressures and highly alkaline environment of curing concrete. This system remains completely dormant until a crack inevitably forms. When physical damage occurs, incoming water and oxygen seep into the concrete matrix, acting as a biological trigger. The moisture rehydrates the dormant spores, causing them to germinate within hours. Once awake, the active bacteria feed on the surrounding calcium nutrient. This metabolic process causes a chemical reaction that precipitates calcium carbonate, the exact same mineral that forms natural limestone. The minerals crystallize directly on the cracked surfaces, growing inward to seal the gap and restore the concrete's barrier properties. By generating its own limestone plaster from within, the material autonomously repairs its structural wounds before they can expand. Transforming a laboratory reaction into a permanent structural feature requires solving a hostile engineering challenge. Freshly cured concrete is an incredibly harsh environment, with a highly alkaline chemical makeup reaching a pH of 13.5, nearly as caustic as industrial bleach. For the biological system to work, the dormant bacterial spores must survive these extreme conditions for decades, waiting quietly for a crack to form. To protect this living payload, engineers rely on 3 distinct encapsulation methods. First, microcapsules isolate the spores and nutrients inside tiny polymeric shells. When a crack tears through the concrete, the physical stress ruptures these shells, releasing the active ingredients at the exact site of damage. Second, hydrogels employ superabsorbent polymer networks. When water penetrates, these gels swell, establishing a moist microenvironment that keeps the bacteria hydrated while preventing nutrients from washing away. Third, lightweight porous aggregates such as expanded clay or shale absorb the bacterial mixture into their internal pore networks. Because these aggregates behave like traditional gravel, they blend into the concrete mix without creating physical weak points. Once water initiates germination, the physical repair process typically takes 7 to 21 days. This healing speed depends on ambient moisture, temperature, and how easily nutrients can diffuse to the active bacteria. In August 2017, the theory of self-healing concrete crossed from controlled laboratory environments into the physical world. In Antwerp, Belgium, contractors poured a solid concrete roof slab for a sewer inspection pit on the massive Oosterweel Link project. This marked the first large-scale structural application of the technology, incorporating a mixed ureolytic bacterial culture directly into the batch. Underground and exposed to constant moisture, the installation served as a critical proof of concept. Over the subsequent years, monitoring techniques like acoustic emission sensors and crack width gauges confirmed that limestone was actively precipitating inside the structural element, sealing cracks under normal service conditions. The testing network quickly expanded across the English Channel. In South Wales, the A465 Heads of the Valleys Highway upgrade became a live testbed for the Materials for Life Consortium, a collaboration between the universities of Cardiff, Bath, and Cambridge. Engineers cast 5 massive roadside retaining wall panels on site. One panel embedded bacterial spores, while others used microcapsules and vascular networks. When traffic loads and freeze-thaw cycles induced microcracks, environmental moisture triggered the self-healing process, reducing crack widths by over 80% within 30 days and preserving the panel's flexural strength. The momentum spread to the Netherlands, where railway operator ProRail and Heijmans Infra completed a pilot railway underpass in Regen in July 2024. By utilizing a bacterial additive developed at Delft University of Technology, the engineers reduced the horizontal steel reinforcement by 50%, lowering the structure's initial carbon footprint while relying on the bacteria to maintain water tightness. Similar commercial pilots are underway across Germany's Autobahn network and bridge foundations, along with full-scale wastewater treatment tanks in Limburg. These institutions are proving that self-healing concrete is no longer a laboratory curiosity, but a early-stage infrastructure reality. Despite successful field trials, self-healing concrete faces steep barriers before it can replace conventional mixtures. The primary obstacle is cost. On a per cubic yard basis, these specialized mixtures price out at close to double that of conventional concrete. This premium is driven by the complex processes of bacterial cultivation, nutrient synthesis, and encapsulation. Beyond financial hurdles, environmental extremes threaten the biological engine itself. While spores survive moderate shifts, temperatures above 40 degrees Celsius slow bacterial metabolism, and freeze-thaw cycles can reduce overall healing efficiency. Compounding these physical limitations is an institutional hurdle. Standardized testing protocols from ASTM, CEN, or ISO remain incomplete, leaving engineers without a clear pathway for code approval. Because infrastructure failures carry severe safety risks, the construction industry remains deeply conservative. Procurement channels and building specifications favor predictable binders over active biological agents. Before this living material can become routine, it must earn institutional trust. For infrastructure managers tracking life cycle costs, self-healing concrete represents a long-term investment measured in decades. Extending a bridge or highway's service life minimizes disruptive maintenance, reducing the demand for reactive patch repairs and the high-emission cement required to produce them. While widespread commercial scaling remains several years away, the technology holds immediate value for high-consequence, difficult-to-access projects, from subsea tunnel foundations to speculative regolith-based structures on Mars. By converting concrete from a deteriorating structural liability into an automated, self-preserving system, the built environment begins to behave like a living network. As global infrastructure ages, the line between raw materials and living systems is permanently blurring. The science is real, but the final hurdle is our own perception. Would you trust a building that heals itself? Subscribe for more deep dives into engineering.